Thank you, Victoria. Thank you for coming on your free afternoon in Vienna. So I want to talk a little bit about the amplituhedron and whether or not it's a positive geometry. And I want to give sort of a little bit of an overview talk. So please don't expect too many details, but ask away if you want to know more. So I already put down the definition of the amplituhedron. So we start with an input data of a matrix, real matrix Z, that is totally positive. So all its maximal minus is positive numbers. Such a matrix defines a rational map between Grassmannians. So what I'm saying essentially is a matrix is a linear map from Rn, Rk plus M, and V represents a subspace, a k-dimensional subspace of n-dimensional Euclidean space, and I just map it to the subspace, which is its image, inside k plus m-dimensional Euclidean space, and this is almost always well defined. Of course, what can happen is the subspace intersects the kernel of this linear map, then the dimension drops, and I'm not in the correct Grassmannian, but otherwise. Maybe this is made up, this convention. I didn't look it up. This might be sort of transpose of what you usually write. I don't remember. Okay, and the amplituhedron, depending on these choices of these three numbers, n, k, and m, and this matrix, of course, is the image of the non-negative Grassmannian under this map, and the non-negative Grassmannian are the k by n real matrices, such that all k by k minus are non-negative real numbers. Okay, so that's a bit of a mysterious set if you haven't seen it before. And the question is this another thing that has mysterious properties, namely a positive geometry? So let me briefly say what a positive geometry is. I like to write it as a triple. So I have an X, which is an algebraic, probably smooth, usually projective variety. And for today, it's just always a Grassmannian. Real, maybe also, I should say real algebraic. This is a semi-algebraic subset. For instance, the amplituhedron is a semi-algebraic subset here, essentially by Tarski's quantifier elimination. And this is really the main thing. This omega is a top-dimensional, is a top-form, rational differential top form. It should be uniquely determined by the semi-algebraic set as a subset of X by a recursive definition of the residues of this form. I will maybe say a little bit more later. It should be unique. I didn't say that. It should be unique with this recursive property of having certain poles. And it's a fairly restrictive condition. So it's a little bit mysterious to expect that such a set always satisfies such a relatively restrictive definition. So having such a top form seems maybe at first sight to be quite a strong requirement. So why would you care about such a thing? And I think there are many different answers to this question. And the physicists have an answer that I can only vaguely paraphrase as, if you do this kind of thing and you say the right words, QFT, blah, 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 then this will compute, this rational top form will compute an amplitude. And the curious thing is that it should be determined entirely by the, what do you call this, kinematic data, I think. Okay, cool. So of a scattering process. For us, as a mathematician, I think it should be sort of completely determined by the set, right? The geometry determines the amplitude is maybe a slogan we can have in this context. And that maybe is then nice because you can do wonderful things. If you understand the geometry, you might make interesting conclusions about the amplitude or not. So maybe that's a rough physicist answer. The maybe plain answer is because it works, right? Surprisingly. And it's mysterious to me why this sort of condition, this seems important, this total positivity of this input matrix is very important for this story to work out. And it's mysterious why. Very hard to say in like 5 sentences why this is. And so maybe the plain answer is because it actually is true some of the time for now, and the conjecture is it's actually always true, at least for nice matrices at mild conditions. Okay, so maybe that's why we can. Okay, so what do I want to tell you about? What are the simplest examples of positive geometries? The simplest examples are polytopes. So X is just projective space. Semi-algebraic set is a polytope. It may be an affine chart, and then we can determine this. And there are, I want to describe 3 different ways you can prove this for a polytope. It's known work by many people, and polytopes are not so hard. And I think we've all tried to generalize every single one of these ways to the amplituhedron, and none have worked out very well so far. There's always something missing. I want to start with maybe the simplest, some, or at least most elementary way of talking about this. And that is the idea of just triangulating a polytope and then having sort of an additive formula for this canonical form. Okay, so I want to start with the polytope. The numbers will be the following. I want this to be a d-dimensional, full-dimensional polytope in some Euclidean space. I will, confusingly, I think this is sort of consistent, call the number of vertices n. I want this to have m facets. Maybe that's actually inconsistent. Should I switch the 2? I think I should switch. So m is anyway bad. Don't think too much about this m. N will actually sort of have something to do. Anyway, so what you're going to do is you're going to triangulate the thing. So where I want my 5 going to be here. So suppose this is my P. I guess it's too small now for people online. Let's make a big picture. And now you triangulate. So for example, any triangulation will do. Do 3 triangles without introducing new ones. So you can, new vertices, you can always do this for polytope. And then it turns out, that this mysterious canonical form of this polytope is just the sum of the 3. Now the question, of course, is how do you compute this omega for a simplex? And for a simplex, you just write it down. For a simplex, going to be roughly up to scaling. You have to pick the correct number. Now I need the facet inequalities. Let's call them AI, BI, EI. Choice. So here maybe X, Y. And you have to sort of choose the correct constant, which should roughly have to do with the volume of your triangle. So the canonical form knows the edge length, knows the volume of your triangle. But of course, I can rescale my inequalities if I want to. So depending on which scalings you choose for the three inequalities, you have to pick an appropriate number. But if you do it very nicely, then the number you have to put is the volume of the triangle. And this works out always in every dimension. You take your polytope, any polytope in any dimension, you triangulate it, you decompose it into simplices. For every simplex, you write down this formula, 1 over product of the facet inequalities. Make this a differential top form, and then up to the volume constant, this gives you the canonical form of the polytope. So it's a positive geometry. Now, there is a little caveat if you want to do this, which is that if you add up these canonical forms, you get something which doesn't have to be positive geometry. So the theorem that is true, which is a theorem that goes back to Nima, Akani, Ahmed, and Thomas, is that if you have what they call, so the slogan is canonical forms are additive. So they have a definition of triangulation of a positive geometry, which maybe I write like this, from 1 up to t. So the simplest case is just you take a sort of decomposition, you write your semi-algebraic set X greater than or equal to 0 as a finite union of other sets, and the interiors should be disjoint, like a triangulation. Interiors of the simplices are disjoint and they meet in facets. So if this triangulates semi-algebraic set, and they are, for example, positive geometries, every one of them, then what you get is what is a little bit weaker. It's a pseudo-positive geometry. That's a thing where you can define a corresponding rational form, but it might not have vertices, for example. And its form is the sum of the forms of the pieces. So the simplest example where this goes wrong, our favorite pizza slices. So you take a unit circle in the plane, you cut it in half, make a set here and a set there. And both of these pieces, they are half a circle, they are simplex-like positive geometries, they're like a triangle, right? If you think of this conic degenerating into two lines, it's roughly the correct thing. Both are positive geometries, but the union is not. The union is the whole circle, it has no more vertices, there's no recursive way to go to dimension 0. So sort of, these forms are nicely additive, but unfortunately you have to put in some extra work to show that globally the thing gives you still a positive geometry. You know the form from such a decomposition that you want, but you don't automatically get that it's a positive geometry. You have to do some extra work. For polytopes, you can do this extra work. And you can actually show, I mean, a polytope has a vertex, right? We all know this, and it has to be the vertex of one of the simplices. So you can sort of do extra things, and it's going to work out if you use this theorem. But this maybe is the main reason why it's not so easy to try the same idea for the amplitude. Even if you do this, which I will briefly mention, you can sort of generalize triangulations to tilings. And then hope that you can write down the canonical form of each tile, you can sum them up, but then what have you, I mean, you have a formula, which is great, it's good to have a formula, but are you done or not? Not so entirely clear. Okay, so that's maybe the problem in this story of triangulating. So the idea maybe you get from this is what we now call tilings. pseudo or not. I mean, usually they're not. There's been a lot of work on this. So this goes back to even the BCFW recursion that suggested there should be such a thing, and then cluster algebras have gone into actually proving that this works. So this works quite well for m equal 2. Matteo is here, he's an expert for this. Lissa, Sherman, Bennett has worked a lot of so they have a few joint papers, I think, on this topic, and it works out nicely. And this is one way to get a formula, I think. I don't think you've written the formula anywhere, but I think it's a way to actually get the formula if you want to compute the canonical form. Maybe not directly the best thing to prove it's a positive geometry, at least so far. M equals 4, there's also work by other people. Okay. So I guess the philosophical point I wanted to make is nice to compute, maybe not entirely obvious how to prove the claim in this strategy. That was my part number 1. Have you seen, I said? Questions, comments? Did I forget something? So that's one way you can do it. Hope to do it. And this has a very combinatorial flavor. So let me try to move on to sort of more geometric flavor, which is via adjoint hypersurfaces and polytopes. This has to do with the dual volume function. And here, sort of the rough idea is the following. So the first statement I want to write, I don't know how to attribute this to. I'll call it a folklore theorem. Is if you start with a polytope, and you look at its canonical form, and up to choosing the correct scaling of things, this is the so-called adjoint hypersurface of the polytope by the product of the facet inequalities. And then you decorate this to be a top form. And this thing is defined by interpolation. This I want to motivate via example. So it interpolates the so-called residual arrangement of the set. So in the same picture as before, I learned that I should draw. This is my polytope, and I start taking residues of this form along the boundary lines. I will get poles at every, so ignore the adjoint for now. I just want to look at the form 1 over product of the 5 lines. If I take a residue of this form along one of the lines, I will get poles along every intersection point with every other line. So draw 10 points. Okay, and in the recursive definition of a positive geometry, you want the forms to always recover the boundary. If you take a residue along one of these boundary lines, say, for instance, this one here, and the one form I get on this line should recover these 2 points only as poles, and the others should disappear. And this is the job of the adjoint. So the others I should have used a different color. We call residual the sort of spurious poles of this form that you need to get rid of. You need to correct this by the numerator of this canonical function that you put in front of the form. This is supposed to be a conic. I think it will be a hyperbola in my picture. So there is a unique conic through these 5 points, and that's the adjoint. Adjoint interpolates or the residual arrangement. These are poles that it's not supposed to have. Right? So the corrects so that you have the right poles recursively. Okay. So you can try to study this instead, right? You can try to study the adjoint polynomial, write this formula, and check that what you get is the canonical form of a positive geometry. Of course, then the question is, what can you prove about this thing? And the main thing you want to prove is that it's uniquely determined by this interpolation condition of interpolating the residual arrangement. Because you want the form to be unique, so that's a good start. Once you know the adjoint polynomial is unique, you have a very good candidate. That's a more global point of view. Not depend on any choices. So then the task is to study what is the residual arrangement of this amplituhedron and does it uniquely determine the adjoint hypersurface. So even for polytopes, that's not entirely trivial. There's a paper by Kathleen Kuhn and Christian Ranester where they actually prove this. So a simple polytope has a unique and I write this word. Hypersurface. So simple polytope, I mean even more actually. So they want a simple facet hyperplane arrangement. So when you look at the hyperplanes, there's a risky closure of the facets of these polytopes. And in every intersection, in every subspace that is the intersection of such hyperplanes, you want exactly codimension of this linear space many hyperplanes to pass through it, not more. It's a transversal intersection kind of condition. And in that case, so simple polytope just means this on the boundary of the polytope, but actually you need it outside of the polytope. And then you can prove that containing these linear spaces, in general, these are linear spaces that are away from the polytope, uniquely determines an adjoint hypersurface of degree, what was my choice? N facets of degree n minus d minus, which comes from the canonical divisor of projective. Yes. Well, yes and no. Okay. So suppose you take the cube, standard cube, in R3, by which I mean, for example, you take let's do minus 1, 1 cubed. It has parallel facets. So in P3, okay, let's study the residual arrangement in P3. I claim it will look like this at infinity. So because the facets are parallel, they intersect in lines. These are residual lines. But since they are parallel, all three of these lines will be at infinity and they will form a triangle. The adjoint should have degree 6 facets, -3, -1, should be a quadric in P3. And it should contain these 3 lines. So in this example, there's a lot of quadrics that do that, every multiple of the hyperplane at infinity. Being a positive geometry picks exactly one of these. And that's with this connection of dual volumes. So the one you should pick in the context of positive geometry is the square of the hyperplane at infinity. And one way to see this, so the adjoint is not unique as a polynomial in this case, but in the context of positive geometry, there is a unique best adjoint to choose. One way to say it is via dual volumes, which I didn't want to say, but it's because it's a dual volume function, this omega, so this picks a unique one, so that's sort of Warren's work and generalized barycentric coordinates and so on. Another way to do this, which you might appreciate more, is to wiggle the cube, the facets, so then these become 3 skew lines. They determine a unique quadric, and whenever you degenerate, in whichever way you choose to the parallel cube, you always get X cube. So the degeneration picks a unique adjoint, even though in the degenerate configuration there is more than one. Another way to say it. Yes. So they also prove that you can do this limiting procedure and it gives you a unique one, but another way to do it is by, if you have non-normal crossing, in this context, you know that the adjoint has to not only contain it, but has a certain order of singularity. And if you do this very carefully, then this is also the correct interpolation condition. Here you have to be singular in these 3 points, and that also chooses this. So there is also a way to write a unique interpolation condition in the non-simple. Okay. That is the polytope story. Okay. So then we try to do this for the amplituhedron in the first non-trivial case. This is a theorem I managed to prove with Christian, Barnestad, and Simon. So we did this for k equal to m equal 2. So if you don't remember the notation, what this means is that the amplituhedron that you get, so it is any number of particles, inside the Grassmannian of lines in P3, so the Grassmannian 2,4 is a quadric in P5. And we did this relying on previous work, for example, by Thomas, figuring out what exactly are the faces of this amplituhedron, what exactly are residual things, and then we convinced ourselves that there is a unique adjoint for a generic matrix Z. So you need certain Schubert conditions to be generic for this argument to work. Let me try to sketch how this works. And after we wrote this paper, we decided that we would not try this for higher M and K because it's time. But it's a valid strategy. You can try to show that the amplituhedron is a positive. So what do you need as an input? So first of all, you need sort of the facet arrangement. In general, we like to call this the algebraic boundary, which has, in this case, n components. I like to write them as Chow forms, lines, n, cyclic one, okay, so what does this mean? So you have this Z matrix, which is something n by 4 matrix, 4 by n matrix, let's say, and the Zi's are the columns. They are points in P3. And what I mean by this is you take the line spanned by these 2 points in P3. That's a line. The general line is Q to this line. The Chow form collects those lines that intersect the line 1, 2. Physicists like to just write 1, 2 times. The determinant of a 4x4 matrix. Okay. So we know, so these play the role of the facet hyperplanes, and they are Schubert hyperplanes. So these are hyperplane sections of the Grassmannian that are very special. Schubert hyperplanes. So they have dimension 3. Okay. So what you now have to figure out is what are the residual things. So you might have to intersect 2 of them. Turns out that if you intersect 2 of them, that's not residual. What you have to do is you have to intersect 3 of them to become sometimes residual. And the so-called, so the residual arrangement in this example, the union of certain conics which I mean smooth curve of degree 2 that are contained in some P2 and some lines. And this reducible curve is connected. This connectedness is important because intersection of this connectedness turns out to be extremely helpful because it suffices in the end, in the proof, to interpolate the adjoint hypersurface that we want in all of these intersection points. Residual zero-dimensional locus at a bunch of points. And if you know it at these points, then it automatically, because of the combinatorics of this configuration, will vanish on all of the lines and on all of the points. So it turns out that you just have enough intersection points. Oh, let me see. Adjoint polynomial will have degree n minus 4 roughly, so you have like 2n minus 8, 2n minus 7 points on each conic, or it's an argument like this, right? You have just one more point that forces the entire equation to be 0. You have maybe n minus 3 points on each line, so exactly one more than you need, and so it forces vanishing on the entire. So it's kind of nice, but it's intricate to write down all of this combinatorics, to find all of these residual lines and all of these. So we didn't try this, or let's say maybe k equals 3, because then it's a little bit too much of a combinatorics for large n. Okay, but this sometimes works as well. Once you have the adjoint, I didn't write a claim, huh? Has a unique adjoint hypersurface for generic disease. Once you have this hypersurface, you write down the guess like this. You take the adjoint hypersurface, you divide by the equations of these Chow forms, and now you have to check the recursive condition. And again, so for the residues in dimension 0, if you know what a positive geometry is to be plus minus 1, we again use so that some skeleton is connected to global residues here. Okay. So what's the downside of this? The downside is that you really have to sit down and figure out what is this residual arrangement. So the canonical divisor is class minus 4 times the Schubert class, right, in dimension 1. So you have to, and we have n equations, so it has to be class n minus 4. So locally it will be, if you don't sort of put anything, hide anything at infinity, it will be an equation of degree n minus. Okay. So the downside is you really have to sit down and every irreducible component of the residual arrangement, you have to understand how they how they intersect, how they interact geometrically, so you need a lot of data. It seems to me that you need to understand this, quite detailed understanding of all of this, be able to conclude uniqueness of the adjoint, and then you actually have to also sit down and check the poles. Requires a different kind of input, also quite interesting. Also good. Let's try something else. Okay. We might also try something else. This week we had Clément's talk about mixed Hodge theory, so maybe you try this. Brown Dupont framework, based on their paper of genus zero pairs. Let's see what we can do using this. So this is a slightly different thing. So here you consider pairs. Okay, so this is a nice variety, maybe compact, maybe let's say projected, smooth. Here you don't need real. Let's say Y is a divisor, it can be a subvariety. Divisor for simplicity. Inside X. How to connect it to what I did before. Naive thing to try, and I will comment on whether or not this is a good idea. Is to try, you take an amplituhedron inside its Grassmannian, and as a divisor, you take the boundary, the facet hyperplane. That's one thing you can try to apply this to, but as we will see, there are also other choices that might be better, because this choice is not always. Okay, so then what you need for the machine to work, you need to have this condition that the genus of this pair is equal to 0. So that's some condition. You have to sum Hodge numbers, those and those. I choose them correctly, John. You do like minus P0 in homology. I want the cohomology, so I think I do P0, which is the same as 0Q or something. Anyway, so you sum some Hodge numbers. I don't expect anyone to know particularly well how to do it, so I will try to give you some other tricks of how you can try to estimate this. But this is sort of the input for the setup to apply, right? So otherwise, you have to think for yourself and vary the setup slightly. If you just want to use it out of the box, you have to check. Okay, so just a few tricks to compute this. So there is no pair, and this is just the genus of the thing. If it's a Riemann surface, smooth algebraic curve, compact. This is the same as saying that the curve is P1. The same is true in positive geometry. If you want to be a curve, a positive geometry on a curve, it has to be P1. That is the uniqueness of the omega of the canonical. That is plausible that we might want to consider positive geometries on P1 only. That's good. And then there are some tricks. I don't want to go into too many details. So if you make the correct assumptions on x and y, then one way you can try to compute the genus is if you have x, and let's say I have a divisor y with components, irreducible components d1 up to dm. You can sometimes estimate this by why did I do m? Okay. By the genera, I guess, of the intersections. These divisors. Then you just compute the genus of some variety, and if you make the correct assumptions, that will give you at least an upper bound, so then you don't have to deal with a pair, you can compute genus as a variety. So I will try to motivate the things I say by just using this, and then caveat, to actually use this, you might want to check their paper that the assumptions are correct. So for example, if we do this for a polytope, Moore briefly explained this in his talk on whatever, Monday, no? So for polytope, you can just take the algebraic boundary. So you take as x projective space, as y you take the hyperplanar, facet hyperplane arrangement. Then this will actually make a genus zero pair because of this formula. All right, so say you have a polytope. Put it inside projective space, and you do D, so this is X. Y is the facet hyperplane arrangement. If you now just put some mild assumptions and use this formula, then the genus of x comma y bounded by all intersections of these facet hyperplanes. For some reason I now call H. And these are linear spaces, so they're genus zero variety, so you should get zero. Okay. All right, so let me do a few more genus computations before I tell you what the theorem then actually is. So let's try to compute the genus in this example. So this is amplituhedron k equal to m equal to. And let's do it like this. So I take the Grassmannian 2, 4. And I take y, e, I changed it anyway, to be the union of these Chow forms. I claim this is still a genus zero pair. And let's try the same formula. Let's not worry about assumptions. So then you get the genus of the Grassmannian. Grassmannian is a smooth rational variety. So this is plus the sum of the genera of these Chow forms. In this example, they become quadric hypersurfaces in P4. why this is here. Right? Quadric, they are singular, but that's not it. They're cones over smooth quadrics in P3, and the quadric in P3. That's good. Then we take the intersection of two of them, I not equal to j, genus of BI intersect. Okay, so this will be something 5, 4, 3. This is in P2 now. I did this wrong. This is, wait, what? Good. Good. So this will be something in P3. Okay. This again will be, these will also be quadrics in P3. They're either smooth or singular, depending on whether I or j are adjacent to each other. Hilbert condition. Fine, it's also 0. And you do 3 of them, and 4 of them make a point, which is 0. Here again, these are quadrics. These are either smooth conics in P2, or they are 2 lines. Okay, so you can just, in this case, really, because Grassmannian is one quadratic hypersurface in P5, and you intersect with hyperplanes, this works out very nicely, and you get a genus 0 pair. And essentially, if you do it this naively, this is the only case when this works. So what does this buy you? Okay, so now we know some examples where you have a genus 0 pair. The theorem says if you have a genus 0 pair, you can sort of, instead of worrying about the canonical form, you can worry about topology. Maybe one way to briefly summarize the statement. So the theorem says something like this. So if the genus of the pair is 0, then instead of worrying about a canonical form, which is an element, how do I want to write this? Is a thing here, if you want, right? It's a top form with logarithmic singularities along the boundary. That's what the symbol essentially means. That's sort of one place where you use this. This is mixed Hodge theory. This is really represented by a differential form as we like it. This. And this is the same. Should have put things, no? No. Need to decorate this with zeros, right? 0, 0 parts. Why do you put this usually here? Okay, very good. So these are the things so this is where a canonical form would live. But this is a topological thing now, right? So you can worry about your semi-algebraic set, for example, as a class in here. And then this isomorphism will output the canonical form for you. And you can check if it's a canonical form sometimes by just looking on this side. Topological side, you can worry about whether or not your thing is positive geometry with the recursive property of the canonical. That's maybe the point of view I want to take here. You need a little bit more than just this. You need also other things to have genus 0. If you go down, by residues, I think. But this is roughly sort of gist of this result. So instead of computing the canonical form, which is sort of what we've always tried to do, and then checking the recursive property, you can try to just study the topology. I think that's the main takeaway from this result for canonical form in the Akani-Ahmed by Lamb sense. Exactly. You need sort of these strata that you look at, I think, for this to exactly match the canonical form definition to also have genus be a genus zero pair. I haven't thought this through in all detail, but I think that's what you want. You want this to work for every thing if you go down the boundary stratification, but then it suffices to just look at it logically. And then it doesn't give you a way to compute this directly, only sometimes, but it tells you that there is a canonical form. Then you tile it and compute it via tile. That's what I would do. You prove that it has one, and then you tile it. Feel free to do other. Okay. So let me tell you briefly. We tried this first, we wanted to prove that amplituhedron and the Grassmannian and the algebraic boundary of an amplituhedron make a genus zero pair. Then we tried this for a while, then it didn't work. It turned out to be wrong. Let me give you one example where this goes wrong and why this can go wrong. But in a way that's not really sort of crucial, in a silly way, if you want. So the simplest example we have found so far to illustrate concern we found is the following example. I briefly mentioned on Monday. I want to make a cube, slightly curvy, funny cube. I will attempt to draw a picture. So this is a picture in P3. I take a cubic surface, which looks nothing like this, but I will draw it like this. And a cubic surface in P3, a smooth cubic surface, contains 27 lines. You blow up P2 in 6 points, okay? So let me draw. These might plausibly look like lines, and now this will break the picture. So I take 4 lines on the cubic surface in this configuration that you can do. If you like P2, I can draw a picture in P2 that illustrates this. And so I want this, right? This is now a cubic surface. This is curvy, but this cuts out a quadrilateral on it. That is one facet of my cube. And now I just make a plain old linear cube out of it by adding linear equations. This is my front facet. This is just a hyperplane. Facet in the back. Practice. This picture is a mess. Hope you see what I mean. Is it cube now? I think so. 1, 2, 3, 4, 5, 6, 8 vertices. You see a cube. So it's like a linear standard cube, but one facet is a little bit curved. Now what this does, so this looks, this should be a positive geometry, right? Rational components, it looks like a cube, this is a genus zero variety, this should be philosophically speaking. Okay, so what happens with the residual arrangement? The residual arrangement contains the intersection of this cubic surface and this opposite facet, right? So the cube makes 3 lines. This is one of the lines, but it's not a line. Okay? What it is instead is this. Nothing is straight anymore, okay? We'll actually make a genus 1 curve. Complete intersection. You can easily arrange this in such a way that this is an irreducible smooth intersection. Then it's a plane curve, smooth curve of degree 3 that has genus 1. Okay? We'll call it, even if the number theorists hate me, an elliptic curve. Okay. And if you use this kind of formula, maybe we pretend that things are even nicer and this is actually equal, and it turns out that this will make a genus 1 pair, right? In this case, yes. In general, no. We have 5 linear hyperplanes and this cubic surface, and this makes a genus 1 pair. But, and then we set down, we did the adjoint hypersurface, and we can write down omega of this cube, call it C. This is a quartic adjoint, I think. Is that true? This is 5 plus 3 minus 4 is 4, yes. So quartic over equation of S times L1 5 dx1. So you can explicitly compute the adjoint hypersurface, then you can check that this makes a positive geometry in the recursive. So how does this, why, what's the thing? And then Clément pointed out that we should be more clever. This is maybe stupid, don't do it. Okay? So because this is off my cycle, right? Topological, so off my semi-algebraic set. What I can do, there's different things you can do, but if you want this to fit, so the easiest thing you can do, did I give this curve a name? Let's call this curve E. So you can just get rid of the curve, just blow it up and it goes away. So the ambient variety you should look at is just not P3 maybe. So if you do, call this X? No, okay, X, so you blow up P3 along the curve E, and then you take the strict transforms of these things as a divisor here, and this will make a beautiful pair of genus 0. These things are birational to my picture, and there's an isomorphism outside of the curve, right? So my set stays untouched. My set locally still looks exactly the same. So this was, in this sense, artificial. This curve sort of, if I just make it a little bit Zariski small, which is very big. If I make it Zariski small, the problem goes away, my set looks exactly the same, and I can write down the canonical form on this X. So why does the problem go away? Maybe if you're not super familiar with the blow-up. So what happens if you blow up this intersection is that you separate out the intersection of these two components into a component of this strict transform of the cubic surface intersecting the exceptional divisor, and this strict transform of this plane intersecting. But these two components won't intersect anymore. And this exceptional divisor, if you added this back in, you would still see a problem, right? But we didn't, because we took the strict transforms, not the total transform. So you add an exceptional divisor over this thing, but you don't actually put it in because it doesn't interact with the boundary of my cycle. So you can leave it out. And leaving this thing out is exactly the key that gets rid of. Okay, and this?
Irrational.
Well, you should start with genus 0 variety, right? So the varieties you can't just take any old bunch. So it's important that the cubic surface and the hyperplanes are genus 0 varieties. And it's important that locally, the things I have here in the boundary, so the faces are G0 things. But if the problem is completely outside, you can do this. You just blow everything up and it goes away. This is the idea. Yes. Slogan. You should be fine. If you blow up enough, yes, it should eventually hold. You have to worry a little. It's a little bit more, but that's the slogan. That's the rough strategy. If you have singularities, you have to worry. Fortunately, there's plenty of singularities in the amplitude. You have to worry a bit more, but that's what you want to do. All right, so where does this example come from? Just to wrap up, this is inspired by an amplituhedron, right? We came to this P3 example as a reduction of looking at, for example, if you look at P5 and you look inside at an amplituhedron with at least n at least 10, then inside this algebraic boundary, you find sort of disjoint cycle of 5 lines, right? So these are Z1. You can, inside your cycle of lines, you can choose 5 skew ones, and you just use a junction then. If you intersect these Chow forms, I is 1, 3, 5, 9, and you intersect these people inside the Grassmannian P5. We'll get a curve, and this curve by a junction will have G. But there's a residual curve. So it's off the amplituhedron. So it's a picture like this, essentially. You find a problem, but the problem is not actually local at the amplituhedron, but it's in the residual arrangement of the amplituhedron. So you can, again, get rid of such a problem by blowing it up. That's how this came up in this context. That's how we ended up. For example, we could actually compute to check that there is a canonical form, because this we couldn't compute. If there is a canonical form in this example, I strongly believe that there is, but I haven't, done it. So there is hope that maybe this framework, if we use it correctly, can help us prove that the amplituhedron is a positive geometry, but there's a little bit of stuff. It doesn't, not in the most straightforward way. There's a few other ways we have to. Okay, thanks.